Hi and welcome to video 6 on my integration series, and hopefully you've watched video 5 on the substitution method. I'm going to talk to you today about linear substitution and why it's so important. So I've got two questions for you. The first one is determine the integral of u minus 1 u to the power of 20 du. Is this easy, or is x times x minus 1 to the power of 20 dx easy? Well, it turns out that this one isn't too bad, because I can write this down as the integral of u to the power of 21 minus u to the power of 20. I've just expanded that one bracket to u, and that of course is equal to u to the power of 22 over 22 minus u to the power of 21 over 21 plus c, and that's pretty easy. Second one's a lot harder. I can't expand that bracket over this. It's a product rule, which I can't, there's nothing I can substitute. Substitution won't work, so it's actually quite a tricky question. The best bet really at this stage, without having learned linear substitution, is to expand x minus 1 to the power of 20, and who wants to do that? No one. So let's talk about linear substitution and how it may help. So if you're dealing with a question that is probably linear substitution, you're probably dealing with a question that has a product in it. So there's probably two things being multiplied, and you've probably got one of them that's got a linear component. So if you just had this or this or this, they're pretty easy to deal with, but if you've got a product with them, it gets quite hard. So one of them will have a linear component, and it will almost certainly be the most complex one, where if it didn't have a linear component, it would be quite easy to deal with. So let's have a look at our original example, x times x minus 1 to the power of 20. This would have been easier had it been like this one. X minus 1 wasn't to the power, so the linear term wasn't the complex term. That's the complex term, and it's just a straight u. So instead we've got x times x minus 1. What we're going to do is just do a really simple linear substitution to shift where the complex term sits. So I'm going to say let's let u equal x minus 1. If this was u to the power of 20, life would be a lot easier. And if u equals x to the power of 1, then du dx equals 1, which means that dx equals du. So that's good. Also, if u equals x minus 1, then x equals u plus 1. So now I've gone here and I have swapped dx for du. I've swapped x minus 1 for u, and I've swapped x for u plus 1. And now we've actually got the example that we had earlier. This becomes expanded u to the power of 21 plus u to the power of 20, which becomes 1 over 22 u to the power of 22 plus 1 over 21 u to the power of 21 plus c, and then we just substitute u out for what it's equal to. It's pretty easy with a linear substitution. But we need to work out a way of getting the complex term to be the thing that's not actually within the complex function. And that's where this came in. The nice thing is with linear substitution, that our relationship between dx and du will always be pretty simple. Might not always be 1, but it will always be something fairly simple, just a number probably. Let's have a look at example 2. Now in this case, they're both linear terms. So that makes it a bit trickier, but not that tricky. What we have to ask ourselves the question is, what's the hardest thing about this? And it's this 3x minus 4. So what we're going to do instead is let u equal 3x minus 4, which means that du dx is equal to 3, and that means that du equals 3 dx, or better yet, dx equals a third du. And I'm going to substitute those things back in, but I'm also going to note here that if I rearrange this, I get x is equal to a third of u plus 4. I've written x there, u plus 4. So play around with that. You rearrange that, that's what we get. So I'm going to do these substitutions in here now, and I'll go back to using the colour blue. The integral of 2 times a third u plus 4 plus 3 times the square root of u times by a third du. Now, looks hard, but life's going to get much happier in a second. So 2 times a third is 2/3. So we get 2/3 u plus 4, which gives us 2/3 of 4 is 8/3 plus 3. U to the power of a half is going to help us, times a third du. Now we don't really like fractions, so I'm going to eventually take the fractions out. I'll start with a third. So you want us to be simplifying as you go. That's this third here. I'm cancelling that out. Now I've got in the brackets, I've got 2/3 u still. And then 8/3 plus 3 is 8/3 plus 9/3, which is 17/3. So 13. 17/3 u to the power of a half du. I'm going to take another third factor out because I want to get rid of these. So that gives me a 9th out the front, the integral of 2u plus 17 u to the power of a half du. And that is a 9th integral of 2u to the power of 3 over 2 plus 17u to the power of half du. So all I've done there is recognise that I can expand this. Now that u is a simpler term, I can expand this. And that gives me, I can do these calculations now, a 9th times 2u to the power of 5 over 2, I raise the power by 1, divided by the new power, plus 17u to the power of 3 over 2, divided by 3 over 2, and then plus c. And this is a 9th, just making sure I've simplified this fully, 4/5 u to the 5 over 2 plus 34/3 u to the 3 over 2. Now all in one go I'm going to substitute u back out for what it's equal to and expand that 1/9 in, and I get 4/5 becomes 4/45 u, which is 3x minus 4, I believe. Yep. To the power of 5 over 2 plus 34 over 27, 3x minus 4 to the power of 3 over 2 plus c. Now it looks complex. It's not that bad really. The integration we had to do wasn't that bad. It was just a polynomial based integration with a square root function to make it a little bit more complex. And we've come out with a way of actually integrating that we didn't have before, not for a function like that. So there's linear substitution, an example, and just the methodology behind it. All the best.